Hello there, former, current, and future students. This is Professor Hickey. I am putting up this set of 5 videos with an aim towards getting you guys coached up on reaction rate kinetics. This is chapter 14 of the TRO textbook. It's a topic that's no longer part of our Chem 121 curriculum. It's something that going forward we're going to expect students to have seen in Chem 120. But I do understand that it's a bit of a ragged edge right now. Some students took Chem 120 earlier than this past fall, and so as a result, some of you might be coming in without this bit of knowledge. We're going to be using it in 2 ways, this understanding of how the rates of chemical reactions depend on things like concentration, how they depend on temperature, how they depend on activation energy, and other aspects of the energetics of a chemical reaction. In Chem 121, we're going to use it as a starting point for our discussion of equilibrium. We're also going to use it when we get to nuclear chemistry because we discuss a little bit the kinetics of nuclear decay, which is a very specific type of kinetics that we'll be discussing as part of what we do here. As I go through the PowerPoint slides and some practice problems, there will be moments where I ask you to pause the video and think over the answer to something. I really encourage you to do that so that you're not just getting information from me without tossing it around in your brain just a little bit first. Trust me, it sticks way better that way. So when that happens, just hit pause and think it over, come up with your hypothesis, and then you can just restart the video and I'll jump in. But I don't want to waste YouTube seconds sitting around like Dora the Explorer, so I'm going to ask you to take care of that on your end. Additionally, there will be a few problems that I'm going to put up as part of a Canvas quiz where you can show me what you've come up with for your answers and check them to see if they're correct or not. That quiz should be available for sure by about the middle of the week of January 13th, perhaps a little bit earlier than that, if I'm able to get it done and get the Canvas site ready for prime time. But one way or another, that'll be up for you guys to work through, and if you're just feeling impatient, feel free to email me at jhickey@dvc.edu for any questions you might have about any of this, or for that matter, to see how you did on those problems if the Canvas thing isn't up yet. Without further ado, let's move on. We're going to dig in here with the knowledge that chemical reaction rates, we know from some experience, the reactions don't tend to happen all at once. We've had experience with this in just a couple of things, but I'm going to call your attention to the calorimetry experiment you would have done in Chem 120. In that lab, you did a few reactions where you mixed together acids and bases both in the aqueous phase, and those reactions seemed to happen almost instantaneously. The first reading you took of the temperature, it was already at its peak, and it declined from there. However, when you did it with solids, it was no longer quite so quick of a process. You had to wait a few minutes for the solid to completely dissolve. And there are also plenty of aqueous phase reactions that work this way as well. Molecules need to collide, bonds have to break, new ones have to form, and it requires time for all of that to take place. And so what we're going to be doing is studying how we determine how much time something like this might take, either from data analysis or from theory. In order to define this and to study it, we need to actually say what the reaction rate is. If I define a chemical reaction like this, with A plus B, 2 reactants coming together to yield Y, and you can see there the smaller italic letters are meant to stand in place for stoichiometric coefficients, I can define the rate of this reaction as how much of a species is either consumed or produced over a particular time interval. And the specific number I get will depend a little bit on which of these guys I choose. So for example, the easiest way to deal with a reaction rate might be to say it's the amount of product I make over a certain amount of time. But I could also look at it from the perspective of the reactant being destroyed. If I do that and I want these to come out equivalent to each other, one thing I have to do when I look at A and B is I need to put a negative sign out front because I'm going to be destroying A and B. If I write this delta A over delta T or delta B over delta T, it's going to have the opposite sign of delta Y over delta T. So if I want these to be equal to each other, I need a negative sign there. Additionally, things are going to be formed or destroyed at different rates depending on the stoichiometry. Let's say, for example, that the coefficient in front of A was 2 and the coefficient in front of B was 1. In that case, every time I destroy a mole of B, I'm going to destroy 2 moles of A. So you would expect the rates would be related in the same way, that the A rate would be twice as big as the B rate. And so again, if I want to declare a specific reaction rate number and make it equal to all of these, I have to bear in mind I'd also have to divide each of them by their coefficients. That way, if I take the twice as big A rate and divide it by the 2 that was in front of the A molecule, then I'm going to get the same number I'd get by taking the smaller B rate but dividing it by just 1. Okay? So to check whether that's working for us right here, let's bring it to an actual chemical reaction. Here is NO2 decomposing into NO and oxygen gas. If we're initially consuming NO2 at the rate you see there, 3.0 times 10 to the minus 5 molar per second, and take note, that's how we're going to represent reaction rates, a concentration unit, or perhaps later on a pressure unit if it's in the gas phase, over an amount of time. So how much of the concentration do I lose over that amount of time? The question I have for you is at what rate will I make each of the 2 products, NO and O2? Take a moment, pause the video, and come up with your numbers. Okay, now that you're back, hopefully you went with the NO being the exact same rate, because you notice that the NO2 and NO have the same coefficient. So every time I destroy 2 molecules of NO2, I make 2 molecules of NO. And so their rate of formation and depletion are going to be equivalent to each other. Again, noting that since I'm consuming the NO2, this is the rate at which I'm making the product. As for O2, my hope is that you recognize that should be a little smaller. In fact, it should be smaller by a factor of 2, because of the fact that I'm only making 1 oxygen molecule for every 2 molecules of NO2 that I'm destroying. And so if I start to graph this, we put together a concentration versus time plot, what I'm going to see here, is color-coded in the same way you saw them earlier in the equation, is that the rate at which I'm destroying NO2, which is the green line starting at the top left and working its way downward, is going to be equal to the rate at which I'm making NO. That's the blue line starting down at 0 and working its way upward. Whereas the O2 is a shallower line. You're making it at half the speed. Now, as this reaction continues, the question I now have for you, again, you can pause, is what do you think, just based on your intuition, will happen to the rate of the reaction as I start allowing more time to pass and I destroy NO2? Okay, welcome back. We expect the concentration of the reactant to fall because we can see it. And what that's going to mean to us is that there are fewer collisions taking place between molecules of nitrogen dioxide. Though that fewer number of collisions, because of the fact that there are fewer molecules to begin with, and the partners they need to bang into are further away from them, is going to end up meaning that the reaction rate slows down. And so as that occurs, what we see is a sort of shallowing out of all of these curves. And again, they're going to retain the same ratio to one another, but the result is something that looks like this. I wind up with a curve that is decreasing in slope. I should say decreasing in the magnitude of slope, because it's actually technically an increase in slope. It's getting less negative for NO2. But it's shallowing out, and at the same rate, the NO curve is also shallowing out at all times at the same slope as the NO2 curve. The O2 curve, of course, is just basically the amount of NO you've made chopped in half, and so it also is going at half the rate. And you can see that particularly numerically, at those little marks where they're calculating the slope of an area of the curve. They're basically trying to come up with a tangent line and work out what the rate of change is. And so you'll notice that over 70 seconds, you make twice as much NO as you would make of the O2. The NO2 is a much, much bigger amount, but that's because we're looking at it much, much earlier when the rate was faster. Okay? Now, moving along. We already kind of addressed this, but which concentrations do we expect to have affect the rate of our reaction? Well, that should chiefly be the reactants, because products don't need to normally bang into each other to become products. They're already products at that point. If I want to look specifically at the forward reaction taking place here, I expect pretty much every one of these to start with either an NO2 molecule banging itself against the wall and destabilizing, or banging into another reactant molecule. I will admit, if you get to advanced level kinetics and physical chemistry, there are going to be exceptions to this. But for our purposes, it's usually a pretty good bet that the reactants are the main contributor here. And so that means that our rate law this equation that defines how the rate of the reaction depends on how much stuff I've got, is going to have this general form. Essentially looking at the rate of the reaction as the rate of disappearance of NO2. It's going to be equal to a constant, because we always have constants when we have equations, otherwise it's just a proportionality, times the concentration of the NO2 raised to an exponent. Now that exponent is, at first at least, a matter of conjecture. We don't really have the same ability that you had, for instance, in Chemistry 120, if you took this earlier and learned a little bit of equilibrium. We don't have the law of mass action at our disposal. We can't look at the equation and say, yes, here is the exponent I need for each of the components. In actuality, if I want to know the exact nature of this dependence, it's data-driven. I have to actually do an experiment to work this out because it doesn't necessarily follow that law. Again, if you are somebody who is reviewing kinetics right now and you've never heard of the law of mass action because you haven't done equilibrium, that's fine. That's what we're going to be talking about and learning about in class the first week. So, if I want to do this, if I want to look at a portion of time where the forward rate of the reaction is the dominant one, because we are going to see very shortly that reactions can be reversed, what conditions would I want to look at? What kinds of conditions, what kinds of time periods would I want to look at where that forward rate will dominate? Again, I'll give you a moment to pause and think it over. The main time I want to look at is right at the start of the reaction, before I've made much of any NO and O2, because one would expect the reverse reaction to have the same sort of dependence on the concentrations of NO and O2. If I make them 0, then there's no reverse rate to worry about. There's only the forward rate. And so that's exactly what we do. And we see data like this. Here's a very complex looking reaction that we actually do have a laboratory experiment in our curriculum for, the bromate-bromide reaction. When this reaction takes place, its rate might depend on the concentration of the bromide, the bromate, or the H+, any of those three things. And so to work that out, we need to run a series of experiments where we vary the amount of bromate or bromide or H+ present, and we measure the initial rate, in all likelihood in some sort of spectroscopic manner, watching a color change occur in a reaction vessel. And so to do this, we're going to vary those concentrations. And if you want to make sense of how all this data becomes a rate law, you can look at this in a couple of different ways. One is that you can think your way through it from the perspective of just ratios. And we'll do that first. So a good rule of thumb in experimental science is that if I'm going to analyze a set of data, I want to try to look for experiments where one variable changes, and then I can watch how a different thing changes in response. So to figure out the rate order of bromate, bromide, and H+, I want to look at each of them individually. So looking at bromate, for example, I can see that between experiment 1 and experiment 2, I go from 0.10 to 0.20 molar concentration of bromate, and nothing else changes of the other concentrations. That means any change I see in my initial rate has to be entirely because of the bromate. And so I can see here that going from here to here, that is a doubling of my molarity, and in kind, I have a doubling of the reaction rate, going from 8.0 times 10 to the minus 4 to 1.6 times 10 to the minus 3. If you don't believe me that that's a doubling, go ahead and throw it into your calculator and prove it to yourself. And so that tells me that the bromate, when I double its concentration, I double the other thing. So it is a direct proportionality, and so I would now expect that the bromate is first order. I can do the same thing going between experiment 2 and experiment 3. Notice that between 2 and 3, bromate doesn't change, H+ doesn't change, but bromide does double. And again, going from experiment 2 to experiment 3, I have a doubling of the reaction rate. So by the same logic, I would expect the bromide concentration to also be first order. It's directly proportional to what I had before. Now for the H+, I need to look for a little something else. I need a pair of experiments where H+'s concentration is the only thing changing. It would be tempting to go 3 to 4, because right now that's kind of how the process is felt, but that's actually not going to do it for me, because between experiment 3 and experiment 4, every concentration changed. That's no good. What I need, again, is an experiment where only one of them, the one I'm interested in, changed. And in that case, since experiment 4 has 0.10 molar concentration of the other two things, then I want to start from experiment 1. So going from 1 to 4, I again have a doubling of H plus with nothing else changing in the process. And this time, going from 1 to 4, I now see again a change in the reaction rate, but it is a fourfold increase. And so what that means is that in order to accommodate that, if doubling the H plus concentration causes my rate to go up by a factor of 4, that means in my equation, the H plus concentration must be squared. And again, all of this is proportionality until such time as I add a constant. Now, I know some of you are going to be either unsatisfied with this sort of eyeballing of the reaction rate orders, or you just want something that you can use even if the numbers are a little bit less pretty. And so in order to accommodate that, what we're also going to do is look at a mathematical method for figuring this out. And essentially what that boils down to is beginning with the full rate law equation, but in the absence of any knowledge of the exponents, calling these x, y, and z. And so what we're going to do, and this is going to be a general idea of a lot of how we work with kinetics, is we're going to compare two of the equations that we get and essentially divide them by each other. So for example, if I was looking for the bromate order this time and I wanted to look at experiment 2 and 1, what I might do is plug in those two rates. And I would say, okay, well in experiment 2 it was 1.6 times 10 to the minus 3, and it equaled K times the bromate concentration, 0.20 squared, sorry, not squared, time to the x rather, times 0.10 to the y, times 0.10 to the z, okay? And by the same token, I know that this same equation should hold in the other situation. 8.0 times 10 to the minus 3 equal to k again, times 0.10, sorry, it's 10 to the minus 4 on this one. Made a small mistake there. There we go. 0.1 to the x, 0.10 to the y, and 0.10 to the z. And now notice that because we've worked with two experiments that don't alter the concentrations of Br minus and H plus, it doesn't matter, what the values of y and z might be. They cancel out if I go through here and divide both of these equations by each other. Because if the top one's right and the bottom one's right, then dividing them by each other should give me a good equation. And when I do that, that cancels, k cancels, and what I wind up with now is 1.6 times 10 to the minus 3 over 8.0 times 10 to the minus 4 equals 0.20 to the x over 0.10 to the x, which mathematically is the same thing as 0.20 over 0.10 to the x. And so now if I work out what those ratios are, we can see that this becomes 2.0 equals 2.0 to the x, because that's twice as big as that, that's twice as big as that. And the only way this works is if x is 1. If I make x any other exponent, I'm going to wind up with something iffy. Try this with experiments 1 and 4, and you can prove to yourself that what you wind up with eventually is 4.0 equals 2.0 to the z, 2.0 to the z. And in that case, z has to be 2. You have to square 2 to get 4. The other nice knock-on of this is that we have the ability, once we have a good rate law, to plug in any of the values that we've obtained, any of the experimental concentrations and rates, and figure out what that proportionality constant actually is. And so we'll try that with the first one, because I think it's the easiest one mathematically to do. 8.0 times 10 to the minus 4, and now I'm going to be very deliberate about this. We want the units in place here, so that we can get the right units for the value of K. This is going to be molar per second, as we said, concentration per unit time. And this is now equal to K times 0.10, and we figured out through our work that that's 0.10 to the 1, 0.10 to the 1 again for the bromide, and 0.10 squared for the H+. And at this point, there's nothing else to it. Should note that that's all molar, molar, molar. There's going to be nothing else to this besides dividing all those concentrations on both sides. And so that's going to come to a total of 1.0 times 10 to the minus 4 molar to the fourth. And so my result here is that my K is simply 8.0 molar to the minus 3 seconds to the minus 1. And I know that's a weird looking set of units, but it's just what's necessary in order to make the right side of the equation give us molar per second, once we've multiplied by all of those molarities. Okay, so a quick bit of vocabulary then for what it is we generated. I used some of these words as we went along, but just to make sure we're comfortable with them. What you see here in red on this slide, and denoted here, that ratio of the change in one thing to the change in another, is the reaction rate, the rate at which I destroy bromate over the rate at which the time is passing. As we look over to the blue bit right here, that little K we're referring to as a rate constant. And a rate constant has units. In fact, the units are very educational in terms of telling you a little bit about the overall order of the reaction. Because what the rate constant had to do, we just saw it a moment ago, is it had to cancel out all but one of the molarities that come after it in this equation, so that what you wind up with is a total quantity in molar per second, or molar per minute, or atmospheres per hour, or counts of radioactivity per millennium. Whatever it is, whatever way you're measuring how much stuff you've got, and however you're measuring the time. Lastly, that entire equation as a whole is referred to as a rate law. And we're going to see a couple versions of rate laws. This one specifically is called a differential rate law. We're going to get into what that means in the next video. What we do see from this rate law, and the way we would express this verbally, is that this reaction is first order in bromate and bromide, because we determined that the exponent should be a 1. It is second order in H+, that is, it's not just the rate being proportional to H+, but it's proportional to the H+ concentration squared. And when I add up all of those, it tells me that the reaction is fourth order overall. So for example, if I were to take a mixture that was undergoing this reaction containing bromate, bromide, and H+, and let's say I diluted it by a factor of 2, I just poured in exactly as much DI water as there was solution to begin with. If all my concentrations suddenly were cut in half, the rate itself would drop by a factor of 2 to the fourth, because it would be half as much bromate, half as much bromide, half as much H+, and that's squared. And so I'd wind up with a 16-fold reduction. That overall order is really good at telling you what happens if you dilute something, or if you suddenly changed the volume of the container that it was taking place in. What we'll move on to in our next video is what happens when we treat this with just a little bit of calculus. Don't worry if you haven't had the calculus. It'll be a recognition problem then in that case. But what happens when we do that, so that we can now look at how a reaction's concentrations evolve over time.